Hello everyone! In this session I'm going to teach you about quadratic polynomials viewed as functions. Suppose we have a quadratic function. An arbitrary quadratic function is an expression of the form ax squared plus bx plus c, but I want you to think of something like, say, 2x squared plus 3x, say, minus 7. That would be a typical quadratic function. The graph of a quadratic function is called a parabola. Parabolas look like this or like that. So parabolas may either open up, this parabola opens up, or they may open down. The graph of a parabola is much like a cup, but it doesn't have vertical walls, unlike most cups. Also, a parabola would end up opening infinitely wide, unlike most cups. Yet its walls would be very, very steep as x approaches infinity. In this example, I'm going to teach you one of the most important transformations that can be done to a quadratic function, that of completing the square. Let's take a random quadratic function. In this case, I've selected 3x squared minus 5x plus 1, and let's complete the square. To complete the square means to carry out a sequence of algebraically equivalent transformations. Let me show you what exact sequence. The first thing we do when we complete the square is we identify the leading coefficient. In this case, that is the number 3. Leading, that means that that's the coefficient in front of the highest power of x. So we take the leading coefficient, the number 3, and we factor it out from the quadratic and from the linear term. So we forget about the constant term, so this guy is unchanged, but these two terms, 3x squared and 5x, they are transformed by factoring out the 3. Now, of course, when you factor out 3 from x squared, you're left with 3 and x squared. But what happens with the number 5? What happens with the number 5 when we factor out 3 from it? Well, we get a question mark. So what should I fill in place of the question mark? I'm sure you guessed it correctly. Under the question mark, there must be 5/3. Why is that? Well, when I uncover the parentheses, here I'll be getting, so when I distribute here the parentheses, I'll be getting 3x squared from the first two. But from these two, I'd be getting 3 times 5/3 x, the 3 is going to cancel, and I'll be left with 5x. Now you're going to say, well, how did I know to put 5/3 there? What I did was simply I took, say the number 5 is the number A, the number 3 is the number B, and what you see here is A over B. So you always take the coefficient in front of x, you always take the coefficient in front of x squared, and you divide the two numbers, and you get 5/3. The next step in completing the square is to ensure that we have the number 2. So we need to make sure that we have the number 2 in front of the linear term. Okay, so now the number 2 is not present in front of the linear term 5/3 x. So what do? Well, we multiply by 2 and immediately we divide by 2 to restore the equality. So once again, in the next step we always multiply by 2 and we divide by 2. So that's the next step. Okay, what's the next step? Before we proceed with the next step, let's just simplify a little bit. 2 times 3, that is 6. Now, here comes the real magic, the most crucial element of completing the square. We need to add a certain quantity and subtract a certain quantity so as to make the expression that you see here into a perfect square. So, I need to select the question mark so that this becomes a perfect square. So can I select the expression that you see here so as to get a perfect square? I'm sure you must have guessed it by now. If I were to select the number 5, 6 squares, and I were to add and subtract that number, of course I wouldn't change the expression that I'm saying here because I've added and subtracted the same number, but at the same time I would be able to generate a perfect square here. But why is that a perfect square? Well, let's think about it for a while. What happens when you take the expression a plus b and you square it? What's the formula for a plus b squared? Well, I'm sure you remember that is a squared plus 2 times ab plus b squared. So now, if instead of a we had the letter x, if instead of the letter a we had the letter x, then the letter x would correspond, so x squared would correspond to a squared. Well, the 2 would correspond to the 2 here. Remember, I told you that we need to manufacture 2 in front of the linear term. That's always so that we can make this trick here work with the quadratic. And the letter x here would correspond to a. And what would b then? Well, this number 5, 6 would have to be b, so as to make the expression that we see here match the pattern a plus b squared equals a squared plus 2 times ab plus b squared. Well, if b is 5, 6, then b squared naturally becomes 5, 6 squared. Okay, so we have to add 5, 6 squared and subtract 5, 6 squared in order to complete the square. Now, once again, you can see that the number 5, 6 is going to be shown in 3 places in our computations. Here, here, and here. So we have to see the same number on multiple positions in our computations. Okay, now as we mentioned, this here is a perfect square. And that square is, I'm sure you remembered what we just did. The square that you're going to see is going to be x minus 5, 6, the whole thing squared. So we're having x minus 5, 6, the whole thing squared. Okay, now what happens when we take 5, 6 and square it? Well, 5 squared is 25 and 6 squared is 36, so there we get 25 36ths. Okay? We are essentially done with completing the square, or at least with the difficult part of it, but when we complete the square, perhaps the very final step we do is to distribute. So to take the number 3 and multiply it out by this guy and by that guy. So let's do the last step. So once again, the bulk of our work is done, but let's do a little more. So let me multiply 3 out by the square. And of course, when you take 3 and multiply it by 25 36, right? So when we distribute here, we'd be getting 3 times 25 36. But 36 is divisible by 3, so we can cancel out to 12, right? Because 3 times 12 is 36. So we get here 12. And we're almost done, except that this can be simplified. So 1 minus 25 12ths, that can be simplified. What's that equal to? 1 minus 25 12ths. Well, I'm sure you guessed it correctly. That would be minus 13 12ths. That completes the transformation of completing the square. So as I promised you, I'm going to teach you to complete the square in full generality for an arbitrary quadratic function. Once again, what I'm going to show you is going to look a little bit technical. I do not want you to memorize that. What I want you to do is I want you to train yourself to complete the square on concrete examples and memorize the steps towards completing the square, rather than the rather ugly formulas which I'm going to show you right now. So, to complete the square means to carry out the following algebraic manipulation. let's take an arbitrary quadratic, ax squared plus bx plus c. So here's what we do. First, we factor out the leading coefficient. That's exactly what we did on the previous example. In the previous example, the leading coefficient was the number 3, if you remember. Okay. The next thing we do is we factor out the leading coefficient a from the term bx. So we get b over a. So in the preceding example, that was 5/3. If you remember, b was 5 and a was 3. Okay, the next thing we do is we multiply by 2 and we divide by 2. Okay, so the next thing we do is we add and subtract some magic constant so as to make this expression that we see here into a perfect square. Okay. What was that magic constant? Well, to remind you, the constant was determined like this. Take the number 2, take the number x, and whatever is left between the two of them, that's the number that we have to use. So the number in this case would be b over 2a. So the same number that we see here, that's the number we have to square, and that's the number that we have to add and subtract. Next, we use the fact that a plus b, the whole thing squared, is equal to a squared plus 2ab plus b squared. So in this case, the letter x plays the role of a. So the letter x here plays the role of the letter a. So I'm having a plus b squared, and that is, a squared, and that's the number a here. You can see the same two positions for the letter x, and the letter b, the role of the letter b is taken by the expression b over 2a. Of course, b over 2a, the whole thing squared, is b squared over 4a squared. Okay, and just as in the preceding example, this is the bulk of the work when completing the square, but this expression can be transformed a little bit more by distributing the coefficient a out of this parenthesis. So we distribute the coefficient a to the two terms, and of course we notice that the letter a here is present both in the numerator and in the denominator of this fraction, so we can cancel here we have a squared, we can cancel one of the a's with this a here. And we're left with the final expression which stands for completing the square. So we're left with the expression a times x plus b over a squared plus c minus b squared over 4a equal to ax squared plus bx plus c. So once again, to complete the square means to carry out the transformation. Ax squared plus bx plus c equals a times x plus b over 2a, the whole thing squared, plus c minus b squared over 4a. Now you can see that this expression here is long and difficult to remember. So difficult to remember. So I recommend, rather than memorizing that verbatim, I recommend memorizing the steps leading to completing the square and carrying out those steps every time you need to complete the square. Now, I want to teach you one mathematical term, that of a quadratic polynomial discriminant. So what did we do in the preceding slide? We took the expression ax squared plus bx plus c. So we took that expression and we rewrote it. So we took ax squared plus bx plus c and we rewrote it to a times x plus b over 2a squared plus c minus b squared over 4a. So that procedure, transforming that quadratic here into this, this expression, was called completing the square. That's what we just learned how to do. Okay, so we completed the square like this, but here's what we can do. We can rewrite this plus here into two minuses. Why you're going to say, well, why not? We're allowed to do that. So further justification why we'll do such a weird looking transformation will be given later. So let me just do it for now without explanation. And another thing which we can do is we could take these two terms that we see here and we could put them under common denominator. So how is that done? Well, minus b squared, I'm going to transform it into minus b squared here. And the number c, I'm going to multiply it by 4a. I'm going to divide it by 4a, so in this way I'd put these two in the common denominator. And the two minuses, they're going to give me a plus. So the two minuses here would give me the plus which stands in front of c. So I can transform c minus b squared over 4a into negative b squared minus 4ac over 4a. The next thing I'm going to do is I'm going to take this expression b squared minus 4ac. I'm going to take that expression and I'm going to give it a name. You'd say, why would I want to name such an expression? Well, because that expression is going to appear frequently when we deal with quadratic equations. So I'm going to now take the expression b squared minus 4ac and I'm going to name it. And I'm going to name it the discriminant. So that expression b squared minus 4ac, I'm going to name it discriminant. I'm going to denote that discriminant with a capital D, the capital letter D. And once again, I'm going to declare b squared minus 4ac to be the discriminant of the quadratic, of the original quadratic. ax squared plus bx plus c. Okay? So once again, that expression here, b squared minus 4ac, is called the discriminant of the quadratic function. Okay, so we introduced the notion of a discriminant. Discriminant is simply a number, b squared minus 4ac. Whenever we have a quadratic function, its discriminant is b squared minus 4ac. Why would we care for that? Given a quadratic function, we saw that we can rewrite it in the form something, in this case a, times a square plus another constant. So we can rewrite a quadratic function into the a times something squared. So here we have something squared. That's the object that we see here. Plus yet another constant. So plus yet another constant here. Whoops, I said plus, so I should include the minus. So plus another constant. So what completing the square means is we're taking a quadratic function and we're rewriting it as a square times a constant plus another constant. So from the process of completing the square, we saw that if the quadratic is in the form a times x minus h squared plus k, then h must necessarily be equal to minus b over 2a, right, for that to make sense. And the number k must necessarily be equal to negative d over 4a. So the number k must be equal to negative d over 4a, where d is that magic discriminant, or the number k must be equal to minus b squared minus 4ac over 4a. Now, that expression, rewriting our quadratic function in the form in this form, in the complete square form. So that form is called the standard form of the quadratic equation. So to complete the square means to rewrite the quadratic into standard form. Okay? In the preceding discussion, we learned how to take an arbitrary quadratic, ax squared plus bx plus c, and how, using the transformation of completing the square, to rewrite it into something called the standard form, which is given here, a times x minus h squared plus k. So what's that standard form good for? Suppose that we know how to graph the function y equals x squared. That's the simplest possible parabola, right? So there's no linear term and no constant term. That's as simple as parabolas get. So suppose we know how to plot it, but for some reason we have forgotten or we do not know how to plot any other quadratic function. So could we use the standard form of an arbitrary quadratic function to relate its graph to the graph of the most simple parabola, that of y equals x squared? So can we use the standard form of an arbitrary quadratic to relate the graph of a times x plus h squared plus k to this well-known graph of y equals x squared? So can we relate the graph of this guy to the graph of y equals x squared? Okay, so let's see how that's done using the standard form of our quadratic. First, we notice that if we want to get from x squared to the standard form of a times x minus h squared plus k, what we need to do is we need to take the function x squared and transform it to the function a times x squared. Now, here, with the gray color, I have the original function x squared, and with the red color here, I'm having the function a times x squared. So multiplying x squared by the number a corresponds to stretching the graph of x squared by a factor of a. That's if a is positive. If a is negative, you also need to reflect across the x-axis. Next, in order to go from ax squared to the standard form of our quadratic, I need to replace ax squared with the expression a times x minus h squared. So I'm replacing the argument x with the argument x minus h. As we know from previous discussions, replacing in a function, replacing its argument by argument minus a given quantity corresponds to translating the graph of that function by the quantity that you see here. So if I have replaced x with x minus h, I have translated the graph of my function h units. And finally, if I want to get from the function a times x minus h squared to the function a times x minus h squared plus k, all I need to do is I need to add k units, which corresponds to shifting the graph of the intermediate function with k units. And so finally, I started with y equals x squared. So I started with y equals x squared. That was this function. Then I transformed it to y equals a times x squared. So I squished my function in the vertical direction. Then I translated the graph of my function to the graph of a times x minus h squared. And finally, I translate it again, shifting down k units. A times x minus h squared plus k. So this standard form shows us how to transition from the graph of y equals x squared to the graph of an arbitrary quadratic. That is why all quadratic functions look pretty much like the graph of the function y equals x squared, but with different steepness and with different position of this vertex point, of this tip point, of this bottom of a cup. So when the leading coefficient A is positive, the parabola opens upwards. So we're having a cup which opens in the vertical direction. Mind you that this cup opens infinitely wide, yet its sides tend to be very, very steep as x tends to infinity. So that's a kind of a weird type of cup. Now, when the leading coefficient A is negative, our parabola opens downwards. So we're having an upside down cup. When the absolute value of the parameter A increases, the parabola becomes steeper. So if I'm to take the number A and make it larger in absolute value, my parabola is steeper. And if A is positive, my cup has more vertical walls. This special point is called the vertex of the parabola. That's the lowest point on the parabola if the parabola opens up, or the highest point of the parabola if the parabola opens down. So that point, as we illustrated, its coordinates are h and k. These are the numbers which we obtain by completing the square. The number h is equal to minus b over 2a, and the number k, we found it, that's minus the discriminant over 4a. Our discussion also showed the careful student that the graph of our quadratic function is symmetric across the line passing through x equal to h. So that graph of that quadratic function is symmetric across the line x equals h, because the original simple parabola y equals x squared was symmetric across the y-axis. Symmetric, what does it mean for the graph of the function to be symmetric across the line? That means that if I take a point on the function, I drop a perpendicular towards the line, and then I extend it on the other side of the line so that this distance here equals that distance, then I'm going to land at a point on the graph of that function. So once again, if I start on the graph of the function, I drop a perpendicular to the line, go on the other side, marking the same distance as on the right hand side, then I still obtain a point on the same graph, the same function. So when we move the numbers h and k, when we change the numbers h and k, we simply are changing the vertex of our parabola, right? So the vertex of our parabola is given by numbers h and k. And so when we change them, we're just moving the vertex of the parabola around, okay? But notice that the numbers h and k, they do not affect the steepness of our parabola. So if I were to change numbers h and k, I don't affect the steepness of my parabola, which means that if I change the number b and I change the number c in the expression ax squared plus bx plus c, I do not change the steepness. So the steepness of a parabola depends entirely on the leading coefficient a. In this exercise, we're going to exercise the notion of a standard form of a quadratic function. Let's read the problem. Write an equation of a parabola with vertex at the point 1, 2, which passes through the point with coordinates 2, 3 halves. So there are 2 points in this problem. One is a vertex of a parabola, and the other one is a point through which the parabola passes. So let's see where those points are. First, the point with coordinates 1 and 2. So its x-coordinate is 1. So if I drop a perpendicular from the point to the x-axis, this will be the number 1. And this here would be the number 2. And then we have the point whose x-coordinate is 2. So that is 2. And its y-coordinate is 3 halves. So here we have the number 2, and here we have the number 3 halves. 3 halves is of course 1.5. Okay, so here are our 2 points. This point is the vertex, and this is just a point through which the parabola is going to pass. Now, I claim that entirely from the picture, you should be able to determine whether the parabola opens up or whether it opens down. So suppose that we've already solved the problem. Can you guess whether the final answer is going to be a parabola which opens up, like an upside cup, or a parabola which opens down, an upside down cup? Which of the two is it going to be? I'm sure you guessed it correctly. We're going to get a parabola which opens down. Why? Well, because this is the vertex, so that's the vertex would be the lowest point if the parabola were to open up, and clearly there's another point on that parabola which is lower than the vertex. So that can only happen if the parabola opens down. Its graph should be something like this. I'm freehand drawing here, something like that. Okay. By the end of the problem, we'll draw a computer-generated plot of our function, but for the time being, we should expect to, with hand, I could predict that I should be getting something like this. Okay. So, suppose that we have solved this problem, and we have gotten our quadratic function. Well, once we have our quadratic function, we could use completing the square to write that quadratic function into a standard form. So let's say that we know the standard form of our quadratic function. So our quadratic function is of the form y equals a times x minus h squared plus k. So if we could solve the problem, we could certainly also find the standard form of the quadratic. Okay. Now, let's see what's given to us. We are given that the vertex of the parabola has x-coordinate equal to 1 and y-coordinate equal to 2. But if you remember, the number h in the standard form of a quadratic was exactly equal to the x-coordinate of the vertex of the parabola. So the number h must be equal to 1 and the number k must be equal to 2, right? So the number h must be 1 because that is exactly the x-coordinate of the vertex, and the number k must be equal to 2 because that's exactly the y-coordinate of our vertex, right? So h is 1, that's the first coordinate here, and k is 2, that's the second coordinate here. That's this point. Okay. So using very little information, using only where the vertex of the parabola is, we've already figured out a lot of the parameters of that parabola. In fact, in order to know which parabola we're looking for, all that's left is to find what's the value of the number a. So if we know a, we know the parabola. Okay, let's see what's a equal to. How do we find a? Well, we are given more information. We have not yet used the fact that the parabola passes through the point with coordinates 2, 3 halves. How can we use that in this problem? Well, if if our parabola passes through the point with coordinates 2, 3/2, that means that when I replace the number x with the number 2, this number, and when I replace the number y with the number 3/2, I should get an equality. So I need to have that a times 2 minus 1 squared plus 2 must be equal to 3/2. Once again, the numbers that you see here, 2 and 3/2, those were the x and y coordinates of the second point through which our parabola passes. So now this is a linear equation with respect to the variable a, and it is relatively easy to solve. Indeed, 2 minus 1 is equal to 1, and 1 squared is equal to 1. And 1 times a is equal to just a. So I can remove that. So 2 minus 1 squared is just 1, and 1 times a is just a. And I can transfer 2 to the right hand side. Of course, it acquires a minus when transferred to the other side of the equality. And finally, 3/2 minus 2, that equals negative 1/2. I have found my number a, and so I know the standard form of my parabola. So the standard form of my parabola is y equal to negative 1/2, that's a, so negative 1/2, times x minus 1 squared, so 1 is the number h, plus 2. So we have written an equation of a parabola in standard form. Now we have our answer in standard form, but can we give the equation of our quadratic into the usual form? So what other equivalent answers we could give? Well, we could of course take that quadratic, uncover all the parentheses, and transform the quadratic into the form ax squared plus bx plus c. Let's do that. It's not required by the statement of the problem, but it makes sense to do that so as to see the various equivalent answers that we may produce for this particular problem. So we have negative 1/2 times x minus 1 squared plus 2, and I can simplify that to negative 1/2 times x squared minus 2x plus 1 plus 2, which simplifies further to negative 1/2 x squared plus x minus 1/2 plus 2, or finally I could rewrite that as I run a little bit out of space, so let me continue over here. Negative 1/2 x squared plus x, 2 minus 1/2, that is negative, that is plus 3/2. Okay, and that's my final equation. Negative 1/2 squared, negative 1/2 x squared plus x plus 3/2. And as you can see, this parabola has a negative leading coefficient. So as promised, it's a parabola that opens downwards. The purpose of this slide is to derive the famous formula for the solution of the general quadratic equation. If you have seen this formula before, I hope this will be a good refresher of the theory. And if this is the first time that you're seeing the formula, please bear with me. So, how do we solve a general quadratic equation ax squared plus bx plus c equals 0? Think of an equation like this one. 2x squared, say minus 3x, say minus 7 equal to 0. So something like that. an arbitrary quadratic, set it equal to 0. How do we solve such an equation? The first thing we do when we solve a quadratic equation is we complete the square. Now, in the preceding discussion, we studied in great detail how to complete the square. So I'm going to directly produce the answer for you. We complete the square to get that ax squared plus bx plus c is equal to a times x plus b over 2a, the whole thing squared, minus d over 4a, where d was the discriminant. The discriminant was equal to b squared minus 4ac. So that magic number d is equal to b squared minus 4ac. All other letters that you see, a and b, they are the original a and b from the original quadratic equation. Okay. So this is how we complete the square. This is actually most of the work. But let's see what we can do with this expression. The next thing we do is we identify a, and we factor out a from the constant term. Now see, a is factored out of the quadratic term, but it is not factored out of this constant term. So what we do is we factor a out of the constant term as well. Now when you factor a out of a term which does not contain a in the numerator, you have to divide by a. So this a, when we factor it out of d over 4a, it becomes a squared. So a times a squared, so the product of the a divided by a squared, so the quotient of these two terms is equal to 1 over a, this term here. So we have factored out a. Okay, so we factored out a. What will we do next? The next thing we're going to do is we're going to take the term that you see here, d over 4a squared. So we're going to take that term and we're going to transform it into a square. How can we do that? So I'm taking that term that we see here, d over 4a squared, and I'm transforming it to this term here. So that guy has been transformed to this one. So what have I done here? First, I have taken the expression d and I have transformed it to radical of d squared, right? So I can write that radical of d, the whole thing squared, equals d. So that's what I've done there. And I have transformed 4a squared. I have rewritten 4a squared, this 4a squared, as 2a, the whole thing squared, right? So 2a, the whole thing squared, right? So 2a, the whole thing squared, that is 2 squared times a squared, which is 4 times a squared, which is exactly this 4a squared. So that's what I've done there. So just a reminder, we always need to be careful when dealing with radicals and squares. So just a reminder, if I take radical of d squared, that is not necessarily equal to d, that is equal to plus or minus d, depending on whether d is positive or negative. But when the operations are in the opposite direction, so when I have radical of d, the whole thing squared, then I always get d out. A reminder, this actually works for negative d as well. Radical of a negative number, that would be a complex imaginary number. So that is actually okay. So here, in case d is negative, by radical of d, I mean the complex number, radical of negative something. Okay. So what we have done so far is we have transformed the constant term into a perfect square. Why on earth would we want to do that? Well, here's the trick. By transforming the constant term to a perfect square, we have arranged that what we see in here, the expression here, is a difference of two squares. So here we're having something squared, x plus b over 2a, the whole thing squared. And here again we're having a different expression squared. So we have arranged that the expression that we see here under the parentheses is a difference of two squares. But how does that help? Well, let's see. We know that when we have a difference of two squares, so if I have a difference of two squares, I can factor that. How? Well, if I have a squared minus b squared, that's exactly what I'm having here. This expression here, I can call it a, and the whole thing becomes a squared. And this expression here, I can call it b, and then this whole expression here becomes b squared. So I'm having a squared minus b squared. That's what I'm having. And I remember that a squared minus b squared can be factored as a minus b times a plus b. So this expression that I see here, a squared minus b squared, can be factored. And how does it factor? Well, when we are factoring a squared minus b squared, we get a minus b, so that guy here plays the role of a. That is my a. That is a, that is a. And that expression here, plays the role of b. So that is my b here. And that's my b. And this was my a. There we go. That is my a. So you can see a squared minus b squared is equal to a minus b times a plus b. So we're now in a very good shape. We have successfully factored our quadratic. Now, a factored equation is very easy to solve because see, what have we achieved? We have the product of three quantities, which is 0, right? So we have the quantity a, this second quantity and this third quantity, and the product of those three quantities is 0. But how could the product of three numbers be 0? Well, for the product of three numbers to be 0, at least one of those three numbers has got to be 0. We could also have the case that two of them are 0, or we could have all three of them be 0, but at least one of them has got to be 0. If they're all non-zero, that doesn't work. So there are three options. Either this a must be 0, but that's not the case because a is not equal to 0. When we write down on a quadratic equation, it is always implicitly assumed that a is not equal to 0. So that was an assumption from the beginning, else we wouldn't have been calling this equation a quadratic equation. So a is not 0. So our only chance of having then 0 is to have that either this term x plus b over 2a minus radical of d over 2a. So either this term is 0 or the next term, x plus b over 2a plus radical of d over 2a. So that term here must be 0. So one of the two must be 0. Once again, either this term, x plus b over 2a plus radical of d over 2a must be 0, or x plus b over 2a minus radical of d over 2a must be 0. One of the two must hold. We're almost done. All that remains is to solve. Now we've got two linear equations in x, the left hand one, this one, and the right hand one, and we can immediately solve for x. Let's do that. So I'm solving now this equation for x. I'm taking plus b over 2a and I'm transferring it from the left hand side to the right hand side. The minus becomes a plus, and b over 2a becomes minus b over 2a. And I also need to transfer radical of d over 2a to the right hand side. The minus here becomes a plus. And finally, I can take those two terms. They have a common denominator. Both of them are divided by 2a. So since they have a common denominator, I can put them under a common denominator, which I have done here. So I have put the terms in the common denominator, and there we go. I have solved for x. So x is minus b plus radical of d over 2a. That's my first option. And my second option, for my second possible equation, I can transfer plus b over 2a to the right-hand side. The plus becomes a minus. And I can also transfer radical of d over 2a to the right-hand side. The plus becomes a minus. And I could put the two fractions on the common denominator. They already have a common denominator, so I can combine them to a single fraction. And there it is. There is our solution. So x equals minus b plus radical of d over 2a. So x equals minus b plus radical of d over 2a, or x equals minus b minus radical of d over 2a. Our solution is complete. So let's recap. We started with a general quadratic equation ax squared plus bx plus c equals 0, and we got our two solutions. X equals minus b plus radical of d over 2a, or x equals minus b minus radical of d over 2a. Now, I'm going to remove all things, all of the derivation that we did so far. So I'm going to remove that, and I want us to just stare for a while at the general quadratic equation and its solution. Okay? And now I'm going to take that and I'm going to transfer it to the next slide, and I want to organize our solution into a theorem which we need to memorize. So now I'm going to take that solution and I'm going to transfer it to the next slide. There we go. So I have my general quadratic equation, ax squared plus bx plus c equals 0. And its solutions were given by x equals minus b plus radical of d over 2a, or x equals minus b minus radical of d over 2a. Just a reminder that magical d was b squared minus 4ac. So that magical letter d was called the discriminant. So this was the discriminant. Let me remind you, d is the discriminant. It discriminates between the two roots of the quadratic equation. So that's the discriminant of our quadratic, and it is given by the formula b squared minus 4ac. Okay, so that is our solution. And now there are two possible solutions. So what's the difference between those two solutions? Well, one of the solutions has a plus in there, and the other solution has a minus. Now, I want to do something. I want to introduce names for these two solutions. So the solution that has the plus in it, I'm going to call it x1. So I'm going to call this number, the number that we see here, I'm going to call it x1. And the number that we see here, I'm going to call it x2. So I'm introducing two numbers, x1 and x2. These are the two solutions. One is with the plus and the other one is with a minus. And finally, using that, I'm able to formulate a somewhat shorter version of this formula. So here it is. The solution of the quadratic equation ax squared plus bx plus c equals 0, so the solution of this quadratic equation, is given by the following formula. Its two solutions, x1 and x2, are given by the formula. So the two solutions, x1 and x2, are given by the formula minus b plus or minus, so this symbol here is read plus, or minus, because that's what we had on the previous slide. So plus or minus radical of b squared minus 4ac, or radical of d, radical of the discriminant, the whole thing divided by 2a. So that is our final formula for the solution of the quadratic equation. Ax squared plus bx plus c equals 0 is solved by, its two solutions are given by x1 and x2 equal to minus b plus or minus radical of b squared minus 4ac over 2a. I want you to memorize this formula. If you haven't memorized this formula so far, please do so. Memorize this formula by heart. You will be using this formula a lot in the coming, in the remainder of this session. So we have just illustrated our formula for the solution of the quadratic equation. I want to now discuss the geometric interpretations of these solutions. So the solution of the quadratic equation ax squared plus bx plus c equals 0 is given by the two formulas we recited heavily in the previous slide. Just to remind you, x1 and x2 were minus b plus or minus radical of b squared minus 4ac over 2a, which could be abbreviated as minus b plus or minus radical of the discriminant, the whole thing divided by 2a, where the discriminant d was given by a b squared minus 4ac. Okay. What happens if this discriminant, what happens if the number that we see here, this d, is negative? Well, if d is negative, think of d being something like negative 5, well then radical of d is radical of negative 5, which is radical of 5 times I. This is a complex number. If d is negative, then radical of d is not real, and the quadratic has no real solutions. What does that mean? Graphically, that means that when I plot ax squared plus bx plus c, so when I plot that, then the graph of my function does not intersect the x-axis. So once again, the graph of my function does not intersect the x-axis. I have no real solutions, no real numbers make the graph of that function meet the x-axis. What happens when d is equal to 0? So what happens when this d is equal to 0? Well, then I'm having minus b plus or minus radical of 0 over 2a, right? That's what happens here. But radical of 0 is 0, so I'm getting minus b over 2a. And the two roots x1 and x2 coincide. So our equation then has only one 0 with multiplicity 2. The two solutions x1 and x2 coincide, and the graph of the parabola touches the x-axis. Of course, when that happens, if you remember our factorization of this quadratic was a times x minus x1 times x minus x2. So when that happens, when the discriminant is equal to 0, this becomes actually a perfect square, because x1 becomes equal to x2, which becomes equal to negative b over 2a, and then this whole quadratic becomes a perfect square. In this example, we're going to apply the newly learned formula for solving the quadratic equation to find the x-intercepts of the parabola x squared minus 4x plus 3. So what we have here is we have this parabola x squared minus 4x plus 3. So here is y equal to x squared minus 4x plus 3. So we're having this parabola. We can plot that parabola. That's already done for us. We could plot it with our graphing device. Here's the plot. And we're asked to find the x-intercepts. So what are x-intercepts? Well, the positions where the graph of our function intersects the x-axis. So just a reminder, the x-intercepts, so the places where the graph of our function intersects the x-axis, are precisely the solutions of the equation x squared minus 4x plus 3 equal to 0. So if you want to solve this equation, x squared minus 4x plus 3 equals 0, so the solutions of this equation are the x-intercepts. So asking you to find the x-intercepts of a function is just a fancy way of asking you to solve this. So find the x-intercepts, that's the same thing as solve asking you to solve this. Okay, so when you see a problem stated like this, find the x-intercepts, you're in fact asked to solve an equation. So we need to solve this equation, x squared minus 4x plus 3 equal to 0. That's the equation we're trying to solve. And we already saw that we have a ready-made formula. So there's nothing we need to do in order to solve that quadratic equation except apply the formula. So let's do that. Our two solutions, x1 and x2, are given by the formula minus b plus or minus radical of b squared minus 4ac divided by 2a, where b is equal to negative 4. So that b here, I have to replace it with negative 4. That's negative 4. A is equal to 1, right? So here I'm having 1 times x squared. That's what I'm having here. So A is equal to 1. A is equal to 1, right? Because once again, when I have x squared, it's the same thing as 1 times x squared. And finally, C is equal to plus 3. So that's what I'm having there. Now, minus 4 is plus 4. Minus 4 squared minus 4 times 1 times 3, what's that equal to? That is equal to minus 4 squared, that is 16. 4 times 1 times 3, that is 12. So that is 4. So I'm having a radical of 16 minus 12, which is radical of 4. So I'm having radical of 4 over there. So 4 plus or minus radical of 4 over 2. Radical of 4 equals 2. So I'm getting 4 plus or minus 2 over 2. So that is 4 plus 2 over 2 or 4 minus 2 over 2. Now notice that when we have plus or minus, right, so this here is read plus or minus. This is plus or minus, right? Plus or minus. That's what we're having here. You can expand that using this curly brace. So whenever you have a plus or a minus, you can expand it into a curly brace, and then in one of the entries of the curly brace, you enter the plus, and in the other entry of the curly brace, you enter a minus. So that curly brace is just a different way of saying plus or minus, or one line or the other line. Okay? Now, 4 plus 2 is 6, and 6 divided by 2 is 3. So that's one of our solutions. Now 4 minus 2 is 2, and 2 divided by 2 is 1. So that's another solution. So here are our two solutions, 3 and 1. That solves our problem. So we have found the x-intercepts of our quadratic. So here's the number x equals 1. Here's the number that would be x1, and here's the number x2. Okay, x2 would be equal to 3. We have solved our quadratic equation using the quadratic formula. This example is very similar to the previous one. In the previous example, I asked you to find the x-intercept of a quadratic function, and in this example, we have the exact same formulation. Find the x-intercept of the quadratic x squared over 2 minus x minus 1. So find the x-intercepts of that quadratic, or in other words, solve the equation x squared over 2 minus x minus 1 equal to 0. Now you're going to say, well, why am I making you solve very similar problem types one after the other? Well, there's going to be a small difference between this problem and in the previous one. So what's the first difference that strikes us? Actually, more than one difference. There will be more than one difference. They're not going to be big, but there will be differences. So what's the first difference that we see? Well, we notice that here the coefficient of x squared is 1/2, right? So I'm having x squared over 2, but see, x squared over 2, that is the same thing as, x squared over 2, that is the same thing as 1/2 times x squared. So I can rewrite x squared over 2 minus x minus 1. I can rewrite it as 1/2 x squared minus x minus 1. Okay, so that's how I can start. So that's the first small difference, that the coefficients of this quadratic are a little bit masked due to the division operation, but that's just a tiny difference. That's nothing significant. Okay. Once again, in this problem, we are ready to directly apply the quadratic formula. So we don't need to think much. Once again, we can directly say, well, the x-intercepts are simply given by the formula minus b plus or minus radical of b squared minus 4ac divided by 2a. Okay. What's b equal to? Well, b is equal to -1, right? Because here I'm having negative x, and negative x is the same thing as -1 times x. So b is equal to -1. b is equal to -1, right? So the coefficient of x here is -1. What's a equal to? Well, a is equal to 1/2. So a is equal to 1/2, right? Because I'm having here x squared over 2, which is 1/2 times x squared. So a is 1/2. A is 1/2. Right, that's that 1/2. And what's c equal to? Well, that's easy. C is equal to -1. Okay, so we're done with the formula. That was the whole thing. So let's simplify. The 2's cancel. -1 is equal to +1. And what happens here? Well, let's see. We're having -1 squared minus 4 times 1/2 times -1, which equals, well, -1 squared, that is equal to 1. 4 divided by 2, that equals 2. So I'm getting -2. Here I'm having 1 minus, here I'm having a second minus. So 1 minus -2, and 1 minus -2 is equal to 3. So that whole expression that we see here, that whole nasty expression, is equal to 3. I just simplified it here for you. Okay, so that expression is equal to 3. Well, that's it. We're done. Our two solutions are 1 plus or minus radical of 3. Right? So here's 1 minus radical of 3. And here's 1 plus radical of 3. Okay? There's a small typo on the slide. Please ignore that. Once again, this is 1 minus radical of 3, and this is 1 plus radical of 3. I promised you that there were tiny differences between this slide and the preceding one. Well, the number one difference was that here somehow the coefficient in front of x squared was masked. So the most remarkable difference from the beginning was that the coefficient in front of x squared was rather hidden, and you could now see this second very, very small difference is that, well, in the preceding example, we were lucky to get a perfect square under the radical. So in the preceding example, we were able to simplify the radical that we were getting. So in the preceding example, the term which corresponds to this term here we were able to simplify it in addition, right? So in the preceding example, we had radical of 4. In this example, we have radical of 3. That we cannot easily simplify. So that's the major difference. Okay. And here's our final solution. In this example, we're going to do our last basic application of the quadratic formula. Again, we have a problem formulated the exact same way. Find the x-intercepts of x squared minus 2x plus 3. So here's the quadratic x squared minus 2x plus 3, and we're being asked to find its x-intercepts. Just a reminder, the x-intercepts of a function correspond to the place where its graph intersects the x-axis. And to find the x-intercepts of a function means to set the function equal to 0 and to solve the equation. So I'm asking you to solve x squared minus 2x plus 3 equals 0. Now, if you plot x squared minus 2x plus 3, if you plot it, it's going to look like this. This is an accurate plot. And this is a parabola. We already studied that that's the vertex of the parabola is its lowest point. So we expect from the graph, we expect that there will be no real solutions. We do not see any intersections of the graph of that function with the x-axis, so we expect to see no real solutions. Well, let's see if that is the case. We know that the x-intercepts, so the solutions of our quadratic equation, are found by the formula minus b plus or minus radical of b squared minus 4ac divided by 2a. What's b equal to? Well, b is equal to negative 2. That is our b. Careful here, this minus has got to stay in front of the parentheses. So b is negative 2. A is equal to 1, right? Because we're having x squared, which is 1 times x squared. And then a is equal to 1. A is equal to 1. And finally, we have that c is equal to 3. C is equal to 3. So we're done. We have applied our formula, and that's it. Minus 2 simplifies to plus 2. And what happens with that expression? Well, we have minus 2 squared minus 4 times 1 times 3, which equals, well, minus 2 squared, that is 4, and 4 times 1 times 3, that is 12. So 4 minus 12, which equals negative 8. So that expression that we see in here equals negative 8. And of course, 2 times 1 equals 2. So that's it. We're done. Now, radical of negative 8, that is not a real number. So we have no real solutions. So for no real number, does the graph of our function intersect the x-axis? So no real solutions, no x-intercepts. So our final answer should be no x-intercepts. So we're asked to find the x-intercepts, but our answer is too bad. No x, no such intercepts. Our problem is solved. In this slide, I want to cover an important property of the discriminants. So just a reminder, the discriminant d was, so given a quadratic ax squared plus bx plus c, so given a quadratic ax squared plus bx plus c, its discriminant d was this expression, b squared minus 4ac, the expression that participated under the radical in the formula for the solution of the quadratic equation. So that number d equal to b squared minus 4ac has some special properties. Let the roots of the equation ax squared plus bx plus c, let those roots be x1 and x2. So x1 and x2, they were given by some complicated formula. If you remember x1 and x2, those were minus b plus or minus radical of b squared minus 4ac over 2a. So these one of these guys with the plus is x1, and the other one with the minus is x2. And so what does this slide say? Well, it says, look, if you take b squared minus 4ac, so if you take that expression, b squared minus 4ac, take that expression, then you get the same thing that you would get if you take x1, take x2, subtract the two, square the whole expression, and multiply it by a squared. So you can obtain the discriminant using x1 and x2. So that's what the proposition says. Let's quickly prove that proposition. So in order to prove the proposition, we need to start with the expression a squared times x1 minus x2, the whole thing squared, right? So that's how we start. And we need to demonstrate that that expression that we see over here, a squared times x1 minus x2, the whole thing squared, we need to demonstrate that this expression is equal to d. We need to show that that expression is equal to d. So the expression a squared times x1 minus x2 squared, that is of course equal to a squared times, so let's see, so this is my x1, right? x1 is minus b plus radical of d over 2a, and my x2 is minus b minus radical of d over 2a. So there we go. So let's simplify. Now these two fractions have the common denominator. The denominator repeats. So what's in the numerator can be put together. So I'm having here minus b, and here I'm having minus b. So minus b, that is plus b, and plus b minus b, the two cancel. So I can cancel the minus b here with the minus b there. Okay. So now, here I'm having plus radical of d minus radical of d. Minus with minus gives me plus. So I'm having radical of d over 2a minus radical of d over 2a. But that's radical of d over 2a. Minus and minus gives me plus, so plus radical of d over 2a. And then I can bring those two on the common denominator to get radical of d plus radical of d over 2a. It's just common denominator, and radical of d plus radical of d is of course equal to 2 times radical of d over 2a. So that's what I get. The 2's of course cancel. 2's cancel. Now, when I square radical of d, I get d. Right? So radical of d squared, that's equal to d. Just a reminder, this always holds, right? So the other way around, there was trouble. So radical of d squared, that was plus or minus d. But when you have radical of d then squared, then you always get d out. Even if d is negative, if you go through the complex numbers, when d is negative, this always holds. So no problem there. So radical of d squared, that's equal to d. A squared is, well, a squared. And now the two copies of a squared cancel, and we get d. So let's recap. We demonstrated with a series of equivalent transformations that a squared times the difference of the two roots squared is equal to the discriminant as desired. This shows that the discriminant of a quadratic equation is 0 if and only if the quadratic has non-distinct roots. So if x1, so the discriminant is 0 if and only if x1 and x2 coincide. So once again, discriminant is 0 if and only if the two roots are actually the same root. In other words, the discriminant discriminates between the two roots, and that actually explains why this d is named the discriminant. This is an interesting problem involving quadratic equations. Let's read the problem. Find the values of the parameter k for which the equation 3x squared minus kx plus 1 has two real distinct roots. So let's think about it. In this particular problem, we have not just one quadratic equation. We have many quadratic equations. So of course, you could say, well, here's what we have, 3x squared minus kx plus 1 equals 0, and you're going to say, well, that's just one quadratic equation. Yes, from a certain viewpoint, that's correct. But you could think that for every value of the parameter k, you have a different quadratic equation, which means that you're looking at infinitely many quadratic equations. Or if you will, you're looking at a one parameter family of quadratic equations, a collection of infinitely many quadratics given by a fixed parameter k. Okay, so we have our quadratic equation. We're being asked to say something about how we can choose the parameter k so as to get particular properties for the solution of the quadratic equation obtained by setting that quadratic equal to 0. Okay, but we don't need to wonder that much. See, we already know a formula for solving the equation 3x squared minus 4x plus 1 equal to 0. So we already know how to solve this. How do we solve it? What are the roots of that quadratic equation? I'm sure you figured it out. The roots of that quadratic equation are simply given by the formula minus b plus or minus radical of b squared minus 4ac over 2a. Where, let's see if we understand what that means. This is the coefficient a. This here is the coefficient b with a negative. So negative k, that's equal to b. That's b. It's negative k. And this is c. That is c here. Okay, so that's the formula for the quadratic roots. Okay. Okay, so we found the roots of our quadratic equation. We actually didn't do any math, we just applied the already memorized formula. Now, we need to have different roots. So we need to have that x1 and x2 are real and they are distinct. Distinct here means that when we take the two roots, they are not equal. So x1 must be different from x2, which means that this expression here is not allowed to be equal to 0. So this is not okay. Minus b plus or minus radical of 0, not okay, because if we are having radical of 0, that's 0, and x1 and x2 coincide. So that's forbidden. Okay, so for us to have real and distinct roots, we need to have that whatever's under the radical is positive, right? Because whatever's under the radical, if it's negative, we're having complex roots, which are not real. So we need to have that the expression under the radical, our discriminant, b squared minus 4ac, we need to have that our discriminant b squared minus 4ac be positive. Not 0. 0 doesn't work because when the discriminant is 0, the two roots coincide. Okay, so b squared minus 4ac must be positive. Okay, now the coefficient b is equal to negative k. The coefficient a is equal to 3. The coefficient a is equal to 3. And the coefficient c is equal to 1. This is our c. All right. So minus k squared is k squared, so minus 1 squared disappears. And 4 times 3, that equals 12. And 12 times 1 equals 12. So our equation becomes k squared minus 12 greater than 0. That's a quadratic inequality. How do we solve that? Well, that quadratic inequality is solved by transforming 12 to radical of 12, the whole thing squared. So you get k squared minus radical of 12 squared. Now that factors, that is a difference of two squares, right? So we're having here a squared minus b squared. That's the situation that we have here. K equals a and b equals to radical of 12. So we're having that situation, and a squared minus b squared, that factors, as we remember, as a minus b times a plus b. So that's how this expression here factors. And when we factor it, we get k minus radical of 12 times k plus radical of 12. So that is our factorization. Now this is a factored quadratic, and when you have a factored quadratic, there's an immediate way to solve the inequality obtained by setting that factored expression greater than 0. So what do? We look at the zeros of this expression, k minus radical of 12. So when k equals radical of 12, that expression here disappears, it becomes 0. So we mark the number radical of 12, that's the 0 of this term here. And this term here, k plus radical of 12, disappears when k is equal to negative 12. So when k equals radical of negative radical of 12, so if you replace k with negative radical of 12, that expression here becomes 0. So we mark the 0, so this is the so this expression here, so this is the 0 of that term, and this guy here is the 0 of this term. Okay, so that's how we mark them. And now our two zeros, radical of negative 12 and minus radical of 12 and radical of 12, they split the real line into 3 intervals, those 3 intervals. So here's our real line. What you see here is the real line. So that's the real line. And we have chopped that real line into 3 intervals. Okay. Now, let's think for a while. What happens when the value of the parameter k sits inside this interval? So what happens when k is inside this interval? So what happens when k is inside the interval from radical of 12 to infinity? So what happens when my parameter k is in here? What happens when my parameter k is bigger than radical of 12? Well, let's see. When k is very, very big, so when k is large, so if you select k to be very, very large, so here's my real line, and I'm selecting the parameter k, I'm selecting it to be a very, very large number, a number which is way, way bigger than radical of 12. So when I select k to be way bigger than radical of 12, so k is way bigger than a radical of 12, this is a positive quantity here, so is this one, if k is very large. So altogether, the expression that we see here becomes positive. So the sign of this factored expression is positive. Okay, now what happens when k is less than radical of 12 but is bigger than radical of negative 12? When k is less than radical of 12, so when k is less than radical of 12, our expression becomes, well, let's see, if k is less than radical of 12, that if k is less than radical of 12, that means that this expression here is negative. And if k remains bigger than radical of than minus radical of 12, that expression here is positive. So when k is between radical of negative 12 and negative radical of 12 and radical of 12, then we're having something negative times something positive. So we have altogether something which is negative. So this expression here is negative when k is between negative radical of 12 and plus radical of 12. And finally, when k is very negative, So when k is very negative, so we're in this situation, we're somewhere here, k is very negative, which means that k is less than negative radical of 12. When that happens, we have some negative quantity times another negative quantity. Minus times minus gives me plus. So altogether, I have something which is positive. So altogether, I'm getting a positive quantity. So once again, let's recap. K squared minus 12 is positive when k is inside this interval, or when k is inside that interval. So our final answer is that k belongs to the union of the intervals between negative infinity and negative radical of 12, so this interval, union with the interval from radical of 12 to infinity, this interval here. Okay. Our solution is complete. By the way, let's see if we can get some plots. So what happens when the parameter k? So what happens when the parameter k is say equal to 6? If we select k equal to 6, here's the graph of our 3x squared minus kx plus 1. That's what we get when k is equal to 6. Now what happens if I move k? What is going to happen if I let k be equal to 4? So if I let k be equal to 4, you see that I'm actually pushing the graph of my parabola upwards. What happens when k is somewhere between negative radical of 12 and radical of 12? So if I select k equal to 2, the graph of my parabola is strictly above the x-axis. And now I can continue pushing k. Now, if k is a little bit bigger than negative radical of 12, the tip of the parabola is already close to the x-axis. And as I push k to be smaller than negative radical of 12, again, the graph of my function starts intersecting the x-axis. So this somehow gives us a neat geometric interpretation of the solution of our problem. In this slide, we're going to cover the question of how do we plot a quadratic function, a parabola, by hand, roughly. Here, we're assuming that we don't have a graphic device. When that would happen, usually when we are faced with a problem that asks us to produce a graphically function by hand, or if we are in an exam where we do not have a graphing device on us, if the exam is no calculators. Okay, so let's see how that is done. When we plot a parabola, the first thing we do when we plot a quadratic function or a parabola, the first thing we do is we find the vertex, the tip of the parabola. The next thing we do is we find the y-intercept of the parabola. The y-intercept is simply its x-coordinate is always 0 and its y-coordinate is the value of the function at 0. Next we find the x-intercepts, if any. Next we adjust the size of the axis to fit the whole picture. And finally we plot the parabola freehand by simply connecting the dots. Now, if the parabola has no x-intercepts, we can only use the y-intercept and the vertex, and then we can just freehand our parabola. If a is greater than 0, the parabola should open upwards, and if a is less than 0, that's the leading coefficient, the parabola should open downwards. If the absolute value of a is greater than 1, we should aim to draw the graph steeper, and if the absolute value of the leading coefficient a is less than 1, we should aim to draw the graph flatter. So let's do an example. Let's plot roughly by hand the graph of negative 2/3 x squared plus 7x plus 3. Now, in the end of this slide, I'll be showing you how to do that. I'll be showing you the actual plot, and that will be plotted by computer. But hopefully, following the instructions in this slide, you'll be able to reproduce a somewhat accurate version of this plot by hand. And the version should be accurate enough so that you can get a ballpark estimates of where the graph of the function lies. All right, so let's do that. As said, our first task when plotting a quadratic function by hand is to find out where is the vertex. So, what is the x coordinate of the vertex of the parabola given? I'm sure you guessed it correctly. The x coordinate of the vertex of a parabola, as studied, is given by negative b over 2a. Here b equals 7, so b is 7, that is 7, and a is negative 2/3. A is negative 2/3. Now we can simplify a little bit. The two minuses become a plus, and the 7, the 2 times 2 is 4, and the 3, when it's transferred upstairs, it becomes 7 times 3, and 7 times 3 is 21. Okay, so the x coordinate of the vertex of the parabola is 21/4. Now, the y coordinate of our parabola. If you remember, we studied a ready-made formula for the y coordinate of the vertex of a parabola. But that formula is a bit tricky to memorize. It's relatively long, so rather than memorizing it, all we need to do is remember that to get the y coordinate of the vertex of the parabola, all we need to do is take the x coordinate of the vertex of the parabola, which is negative b over 2a, and put that inside of the formula for f. Now, we're guaranteed, when we do that, to get minus the discriminant over 4a, which is the same as negative b squared minus 4ac over 4a. So we're guaranteed to get that. If you remember, we studied that that is the y coordinate of the vertex of the parabola. If you remember, that was actually the constant term that is obtained when we complete the square. So we know that we have a ready-made formula, but please don't memorize this. So don't memorize that. That's too much to memorize. Just memorize that we are plugging minus b over 2a in place of x. So we're replacing minus b over 2a for x, and we just uncover all the parentheses. Okay, so let's do that. So what we're going to get is, okay, in this slide, let's use the shortcut formula. We know that we're getting minus b squared minus 4ac over 4a, and here b is 7. Okay. A is negative 2/3. And C is 3. C is 3. So that's what we get. Now 3 and 3 cancels. Minus times minus becomes a plus. 4 times 2 is 8. And 7 squared is 49. Those two minuses here become pluses. Those two minuses become pluses. And 4 times 2 is 8. Now, 49 plus 8 is 57. And the 3 in the numerator jumps upstairs, so that becomes 3 times 57 divided by 8. Or altogether, we're getting, 3 times 57 is equal to 3 times 50 plus 3 times 7, which is equal to 150, plus 21, which is equal to 171. Okay, so we get 171 eighths. So that is our y-coordinate. So what happens if for some reason you cannot remember this formula? So you cannot remember that the y-coordinate of the vertex of the parabola is minus the discriminant over 4a. Well, you don't need to actually memorize that formula. All you need to do is compute f of the x-coordinate of the vertex of the parabola. So all you need to do is compute f of 21/4, right? When x is equal to 21/4, we're at the vertex of the parabola. So all you need to do is take f of 21/4 and compute that. Now I'm going to need a little bit of space in order to compute that number, so I'm going to leave a little bit of space here. So let's do it. f of 21/4 is negative 2/3 times 21/4 squared, right? So here is my negative 2/3, and x squared, that's 21/4 squared, plus 7 times 21/4 plus 3. So that gives me, let's see, negative 2 times 21 squared. I happen to have memorized that that's 441. Of course, you can compute it on the side. Divided by 3 times 4 squared. Plus 7 times 21. Now 7 times 21 equals 140 plus 7. Right, because that's 7 times 20 plus 7 times 1, which is 140 plus 7, which is 147. So that's 147 divided by 4 plus 3. So that gives me minus 882 divided by 4 squared is 16, and 3 times 16 is 48. You know what? It may be a better idea here to cancel 2 and be left here with 8. So rather than using 48, I can use 24 here, and here I could use 441. Plus 147 divided by 4 plus 3. Okay, so now I have to put this in the common denominator. So in order to put this in the common denominator, I'm going to multiply by 6 here and multiply by 6 there. In this way, this becomes equal to 24, so I can put these two together in the common denominator. So minus 441 plus 6 times 147 divided by 24. And I also have to put 3 in the common denominator there, so 3 times 24 divided by 24. Okay, so let's proceed. Minus 441, 6 times 147, what's that equal to? Well, 6 times 100 is 600, 6 times 40 is 240, and 6 times 7 is 42. So I get 882. So plus 882, the whole thing divided by 24, and 3 times 24. So I can put things in the common denominator. 3 times 24, of course, this is 7. So the number of hours in 3 days is 72. So that's an easy one. 72 there. So we get 882 minus 441, that's 441 plus 72 divided by 24, which equals, that equals 513 divided by 24. And let's check this fraction. The top appears to be divisible by 3, so I can cancel out a factor of 3. 513 divided by 3 equals oops, it's so 513 divided by 3 equals, I guess 1, then you put 1 times 3, so oops, 1 here, so 1 times 3 is 3, you subtract the 2, you get 2, then 21 divided by 3 is 17, and then 3 divided by 3 is 1, so 171. Okay, so alternatively, you know that 3 times 170 is 510, and 3 times 1 is 3, so when you add the 2, you get that 3 times 171 is equal to 513. So we get 171 over 8, which is exactly the same number that we see here. Now you can see that these computations can be rather laborious. So of course, for the practical purpose of doing this on an exam, you want to use a calculator if you have one available. So you'll be doing these computations when you do not have a calculator on you and you're being asked to plot that function, or you need to plot that function. Okay, we saw that if the x coordinate of the vertex is since the x coordinate of the vertex is 21/4, then the y coordinate is 171/8. Okay, so that means that my vertex, this is its x coordinates and this is its y coordinate. Okay, so now let's compute the y-intercept. The y-intercept of a quadratic function, that's simply the value of the function at 0, right? That's where the function intersects the y-axis. So what's f of 0 equal to? I'm sure you guessed it correctly, 3, right? Because I'm replacing x with 0 here and here, and so you can see that f of 0 must be equal to -2/3 times 0 squared plus 7 times 0 plus 3. Well, all that remains, of course, is 3. So f of 0 is 3. Okay. So my y-intercept is at y equal to 3. Now let's find the x-intercepts. So to find the x-intercepts of our parabola, we need to solve the equation -2/3 of x squared plus 7x plus 3 equal to 0. Let's do that. First, when we solve a quadratic equation, we can clear the denominators on both sides. So we can multiply both sides of this quadratic equation by 3. Now, when you multiply 0 by 3, you still get 0. When you multiply 3 by 3, you get 9. And when you multiply 7 by 3, you get 21. And when you multiply 2/3 by 3, you get 2. So that's what we get there. Okay, so what's x equal to? So how do I solve that quadratic equation? -2x squared plus 21x plus 9 equal to 0. I'm awaiting for your answer. The solution for x is, I'm sure you guessed it correctly, the formula, I wasn't actually asking you to simplify the whole answer, that would be too much to do so fast, but we remember that the formula for solving a quadratic equation is -b plus or minus radical of b squared minus 4ac over 2a. Once again, I want you to memorize that formula by heart. Okay. So here b is 21. B is 21. A is -2. And C is 9. Now it's quite a bit of expression to simplify, but let's not be shy from computations. Let's simplify. 21 squared, that's 441. I personally have the squares of the first 30 numbers or so memorized for the practical purpose of solving exam problems, but if you don't, you can just derive it on the side. So 21 times 21, that's 1 times 21, and then 2 times 21, which is 2, and then 4, and then you add the two things together and you get 441. So 21 squared is 441. And minus with minus gives you a plus, and 4 times 2 times 9, well, 4 times 2 times 9, that's 8 times 9, which is 72. So we get our 72 there. Okay, now this minus, the minus that's in the denominator, it can jump upstairs. So that makes this minus become a plus. And this plus minus, it becomes minus plus. That's just a minor detail. Okay. Now 441 plus 72, that's of course 513. And let's see, can we simplify that a little bit? Yes. 513 happens to be 9 times 57. Let's check that quickly. 9 times 57, that's 450 plus 63, which is 513. Now, how can you factor the expression 513 as 9 times 57? Well, we already saw in our previous computations that 513 was divisible by 3, and then you can continue to factor out, if you remember, 513 was 171 times 3, and you can additionally factor 171 as 57 times 3. So we can do that. Now we can, why should we do such a factorization to begin with? Well, because we can split radical of 9 times 57 as radical of 9 times radical of 57. And now we can simplify radical of 9 to 3. So we get 21 minus plus 3 times radical of 57 divided by 4. And that's as simple as we can get. So, so we have our x-intercepts. So I have copied my x-intercepts here. Here are my x-intercepts. Here's x1 and here's x2. All right. So now by the way, I want to stress the fact that one of the reasons that I'm doing all computations by hand here rather than with a calculator is that I'm assuming that I do not have access to a calculator, right? Because if I did have access to a calculator, I would just, of course it would be a scientific calculator, so I would just plot my function. So it is assumed that I do not have access to a calculator. So it is important to carry out all computations by hand. All right, so now, so let's select our scale so that we can fit the picture, right? So I actually now have to go ahead and plot all of these points on my coordinate axis. But where do I plot them? How large are these points? Well, the first thing is I need to figure out the x-coordinate of the tip of the parabola. Now, 21 fourths, that's approximately equal to 20 fourths, which is 5. So, so that means that I'm going to need 5 ticks. I'm going to need approximately 5 ticks. 1, 2, 3, 4. So 5 ticks for the tip of my parabola. Okay. Now 171 over 8. I need to estimate how large is that number without the use of a calculator. Well, let's see. 8 times 20, that's 160. 8 times 21, that's 160 and another 8. And 8 times 22 is 168 plus another 8, so that's 176. So that means that 171 times 8, so that means that 8 times 21, which is 168, that's less than 171, which is less than 8 times 22, which means that 171 divided by 8 must be between 21 and 22. So it's somewhere between 22 and 21. So 171 eighths is between 21 and 22. Once again, I'm not using a calculator. I'm doing these computations by hand. So, for the vertex of my parabola, I need to, its x-coordinates is 1, 2, 3, 4, 5 ticks away from the origin, approximately 5 units, and its y-coordinate is approximately 20 units. So it's approximately 20 units. Now 20 is about 4 times 5, so I'm going to have approximately the distance that you see here. I'm going to have to mark it 5 times. Whoops, I'm going to run out of space here. So you see that I have to be careful when I select my scale. So if I want to make a good, accurate drawing of my quadratic, I need to make sure that the x-coordinate of the vertex of my parabola is about 1/4 of the y-coordinate of the vertex of my parabola. So this should be taken into consideration when you try to plot a parabola by hand. Okay, so now let's see. There are more things we need to fit in our picture. So before we actually fix the scale of our picture, let's try to estimate this number and that number by hand. Now, 21 plus 3 times radical of 57 over 4. Well, radical of 57, that's a nasty quantity. It's difficult to estimate without a calculator. But we remember that 57, that's not a perfect square, but it happens to lie between 8 squared and 7 squared, right? That's 64, and that is 49. So that means that radical of 57 must be somewhere between 7 and 8. Which means that I can approximate the radical of 57, I can approximate it with radical of 64. Why do I choose radical of 64 and not radical of 60 or something else? Well, because radical of 64 is very easy to compute. So I can estimate radical of 57 with it's approximately equal to radical of 64, radical of 64, of course, is 8. So 3 times radical of 64 is 8 times 3, which is 24. So that's what I get. So I'm getting altogether 45/4. So this number here is approximately equal to 45/4, which is approximately equal to 44/4, which is approximately equal to 11. So about 11 units for this guy. Similarly, this guy, this quantity here is close to 21 minus 3 times radical of 64 over 4. So that's 21 minus 24 over 4, which is negative 3/4. So this quantity here is about negative 3/4, right? Which of course we can approximate it as that should be approximately -1, right? Because our scale will have to fit quantities as large as 20 units, and when you have when you have to plot such a large quantity, it will be difficult to be very precise about small quantities such as -3/4. Okay. So now, so the parabola, the vertex of the parabola is less than 22 units high, and the parabola opens downwards. So what we can do is we can apply a scale. So this distance here is going to be about 22 units. 22 units. Now I've actually used the computer. This is a computer-generated plot, so this is exactly 22 units in the measurement unit of this picture. But when you plot that by hand, you're going to say, well, this distance about 22 units, that's the y coordinate of my vertex, and this distance here is about 5 units. So this distance here has got to be about 1/4 of that distance. So when you actually plot that by hand, you're going to mark this distance here first, and then you're going to mark the same distance, four times upstairs, about four times that distance upstairs. As you can see, it doesn't quite match. When I tried to mark this distance 4 times on the y-axis, I got a bit higher than this point. Well, that happens. Okay. So now it is time for me to enlarge the axis on my picture, right? So if you notice in the beginning, I had selected the smaller axis. By the way, this very much happens when you do when you plot things by hand, right? So when you plot things by hand, you usually select a random scale on your axis. You may even mark it. You say this is 1 unit or something of the sort, and then later on you change your mind and you rescale your picture. So in this case, I'm going to rescale the axis. I'm going to elongate them so that the highest point on my axis is 22 units. That's reasonable because that's the highest point I'm going to have to draw is about 21 units, between 21 and 22 units. A grid of width 3 units appears reasonable. For this grid here, you may actually have grid paper provided to you when you're on an exam. So that may be very easy to achieve, to have a grid paper. And you can select the unit of the grid paper to be 3. Alternatively, you can approximately plot that by hand with dotted lines, and if you spend enough time, you'll be able to get a reasonably good grid. So let's plot all the relevant points. The y-intercept was at y equal to 3, so that's going to be exactly 1 unit on the grid. And now the x-coordinate, so this was one of the x-intercepts. So the x-coordinate of one of the intercepts was -3/4, which we said was about -1 unit. So if this here is 3 units, if this distance here is 3 units, then you have to go approximately 1/3 of that distance and a little bit to the right. So somewhere there, where marked. And then we have to also plot this quantity here. We saw that this quantity was approximately equal to 11. So it's going to be 3 units here, 6 units there, 9 units there. It's going to be 12 units. So it's going to be somewhere here. So this point is going to be somewhere there. Let's see the computer-generated plot. Oh, I was pretty close. As you can see, I would have done actually a good job by hand. And finally, we have the vertex of our parabola. We have the intercepts. It's time to connect the dots. So let me connect the dots right now. Now, I'm going to show you the computer-generated plot, but before revealing it, I'm going to try to freehand this plot, to freehand this, as I would do on an exam. So I'm going to use these points and try to plot everything myself. Now, I'm not using a real pen. I'm using an electronic pen with a tablet. So it is a little bit less accurate than an actual pen, but I'm going to try to do my best. So let's see how I do. I'm going to have a parabola. The tip of my parabola is going to be here. So this is going to be the tip. My parabola is going to open downwards. And it's going to be something like this. And here it's going to be something like that. You can see I did not do a fantastic job. Let me try to fix it a little bit. So plotting by hand is more challenging than by computer. And certainly plotting with a stylus is even more challenging. Let's see, now that's slightly better. And then again here I'm less than perfect, but I'm sure you can do a better job with an actual physical pen or pencil. Well, this is not perfect. This would, if I were grading such a plot, I would not be taking off points. I see that it's not perfect, but you know, maybe your hand is not that steady. Maybe you're not as very artistic. Maybe you're like me. Yeah, so I did not do a very good job. Let's see the computer-generated plot. Here it is. Well, okay. I'm sure you do a better job than me. But if I were grading my own work, I would give myself, you know, I wouldn't take off credit. I would give myself an A- or okay. This is an okay job. Okay, so we consider this problem solved. Just I want to recap for you the rules for plotting a parabola by hand, just to remind you of all the rules. find the vertex of the parabola. So find the x, so x coordinate is negative b over 2a, and then f of negative b over 2a gives you the y coordinate. Find the y-intercepts, that's just f of 0. Find the x-intercepts by solving the quadratic. Then you get your points, and then you actually getting those points on the grid was a big effort. If you remember, we had to do a lot of by hand computations to get ballpark estimates as to where these points are located, right? Because we had to do all of that without a calculator. And once we have all the points on the grid, we just try to freehand them. We try to connect them freehand with our pen, making a parabola-like shape, a cup-like shape, and if we're lucky and we have artistic ability, we're gonna get a good final output. In this example, we're going to solve an interesting problem involving quadratic equations. Let's find the values of the parameter k for which this expression x squared plus k plus 1x plus 2k is greater than 0. So let's find the values of the parameter k for which this inequality holds for all real x. So once again, here I'm having infinitely many quadratics. So for every value of the parameter k, I'm having one quadratic. And I'm trying to adjust the value of the parameter k so that for all values of x and that fixed value of k, I get something positive. So no matter how I choose, so I want to fix k so that no matter how nasty I choose x, I always get something positive. Okay. In order for this quadratic to be positive, what do we need to happen? Well, look, the quadratic opens upwards, right? So this quadratic opens up because the leading coefficient is greater than 0. So if a parabola opens downwards, it always gets to be negative, no matter how I choose its linear coefficient and its constant term, right? If a parabola opens downwards, it always attains negative height. But this is the leading coefficient here is positive, so we're guaranteed that it is, well, let's not say we're guaranteed, but it is possible that we can choose the parameter k so as to make the graph of this function lie entirely above the x-axis. So can we choose k? Can we choose, so can I choose k so that the graph of my parabola lies entirely above the x-axis? So that's what the problem is about. So the leading coefficient is positive, as already discussed, so the graph opens up. So our picture is going to be something like this. So what you see here plotted by the computer is, of course, I have already solved this problem before I started doing the slide. So I know certain allowed values for k, which make this parabola sit above the x-axis, and I've selected one such value of k, and I've plotted for you one such parabola. Okay. So the graph of my function is going to open up, so it's going to look something like that. Now, for the graph of a function to be above the x-axis, it means that the graph does not intersect the x-axis, which means that the quadratic has no real solutions. What are the roots of this quadratic here? Just a reminder, the roots of the quadratic were the numbers that you get when you solve the quadratic equation. So what I'm really asking you is to set x squared plus k plus 1 times x plus 2k. I'm asking you to set it equal to 0 and to solve. So when I'm asking you for the roots of this equation, I'm asking you to solve that equation that you see here. And what are the roots? What are the roots of that equation? sure you solved it correctly. The roots are, well, this is a quadratic equation, so the roots are minus b plus or minus radical of b squared minus 4ac over 2a. Of course, I didn't expect you to already have everything simplified, but I expected you to acknowledge the fact that we have a ready-made formula for finding the roots of a quadratic, and I expected you to recite that formula, minus b plus or minus radical of b squared minus 4ac over 2a. Okay, so for this quadratic to have no real solutions, right, I need no real solutions for this quadratic, that means that this number here must be negative. So for me to not have real solutions, I need to have that b squared minus 4ac, the discriminant, that's d, the discriminant. So I need the discriminant be negative. I need to have that this discriminant here is negative, right, because if the discriminant is positive or equal to 0, I do have real roots. So I do have that the graph of my function intersects the x-axis, and that's not what I want. Okay, so I need to have that b squared minus 4ac is less than 0. Now b is equal to k plus 1, a is equal to 1, because I'm having 1 times x squared, so a really is equal to 1. And c is equal to 2k. So my c is equal to 2k. So, so now I have eliminated a, b, and c, and I'm left with an inequality with respect to k. So let me solve that inequality. And now k plus 1 squared, that's the formula for squaring things, so I'm getting k squared plus 2 times k plus 1. Once again, what am I using? I'm using the fact that a plus b squared equals a squared plus 2ab plus b squared, which means that if I take a plus 1 squared, I'm getting a squared plus 2 times a times 1 plus 1 squared, which happens to be a squared plus 2a plus 1. Exactly what I have here. Whoops! I should have used k rather than a, right? If I were to use k here, I would have gotten what's written over here. Okay. Now 4 times 2, that is 8. So 4 times 2, that is 8. So I'm almost done simplifying. 2k minus 8k, that is negative 6k. Okay. So that expression now I can factor it. That's k minus k1 times k minus k2, where k1 and k2 are the roots of my quadratic. Okay. So what are the values of k1 and k2? Let's see. Can we guess these roots? Okay, let's not guess it. Let's use the formula minus b plus or minus radical of b squared minus 4ac over 2a. So b equals negative 6. A equals 1, because I'm having 1 times k squared here. And c is equal to 1. By the way, notice that I didn't write A, B, and C here because I've already used the letters A, B, and C for a different quadratic, so I shouldn't be using the letters A, B, and C here. Okay, so there we go. We have our two solutions, K1 and K2. Now minus minus 6 is plus 6, and let's check what this turns out to be. Negative 6 squared minus 4 times 1 times 1, that is 36, minus 4, which is 32. So that is 32 indeed. Okay. Now I run out of space. You can see this problem is relatively long, so I run out of space. So what I'm going to do is I'm going to hide. So I'm going to hide some of these formulas. So I'm going to hide this stuff. So all that I'll leave out is my work so far, and I'm going to let me move my work upstairs. Now if you're following this solution on a pen and paper, simply use more paper. So there we go. Here's what happened so far. Here are my two solutions so far. Now let's continue. Now 6 is 2 times 3, and radical of 32, well, 32 is 8 times 4, so radical of 32 is radical of 4 times radical of 8. Why did I do that weird splitting? So why did I split a radical of 32 into radical of 8 times radical of 4? Well, because radical of 4, that is equal to 2. Which means that this expression here is equal to 2, and I can factor out a 2 from here and from there. By the way, that's also why I split the 6 into 2 times 3. So I can factor out the 2 from here and from there. So I can factor out the 2, and finally I can cancel out the 2 as seen here to get 3 plus or minus radical of 8. So these are my values for the parameters k1 and k2. Okay, so I found the numbers k1 and k2. Now I run again out of space, so if you don't mind, I'm going to erase part of what you see here. So I'm going to move my formulas upstairs. There we go. All right, we're almost done. So let's see what is going on. So I need to solve a quadratic. I need to solve a quadratic inequality. So here what I'm seeing is a function of k. So I'm having some function y equal to k plus 1 squared minus 8 times k, right? So that's this expression here. That's a quadratic function. We can also uncover here the parentheses and rewrite it as a proper quadratic function. If you remember, when we uncover the parentheses, that turns out to be k squared. What was it? Minus 6k plus 1, something of that sort, right? So so that function here is k squared minus 6k plus 1, and I can plot it. So I can plot that function, and here is the first solution k1, and here's the second solution k2. And I need to find where the graph of that function, is negative. So, but the graph of that function is negative when k is somewhere here, right? So when k is between k1 and k2, that's where the graph of that quadratic is below the x-axis, which means that this quantity here is negative. So that means that well, you can see from the graph of the parabola, you can see that that parabola is positive over this interval. So over this interval, the graph of the parabola is positive, right? So the graph of the parabola sits above the x-axis. Over this interval, the graph of the parabola continues being positive over here, but between k1 and k2, it is negative. Oops. So between k1 and k2, I'm having a negative value of the quadratic function. So I get that my final answer is that the parameter k must be between 3 minus radical of 8 and 3 plus radical of 8. So finally, I get my answer. The parameter k must be chosen between 3 minus radical of 8 and 3 plus radical of 8. Now notice that when I write my final answer, I'm saying that the parameter k must sit in a certain interval, and I'm using open parentheses. So why open parentheses? Why open interval? Right, so just a reminder, this is an interval, so when I have the open parentheses, they stand for an open interval. But why is this interval open? Well, why is this interval open? Well, because this was non-strict inequality. So when this inequality here is non-strict, so that means greater than or less than, not greater than or equal to, or less than or equal to. So when the inequality is strict, no equality sign, strict inequality, then I have to use an open interval for my inequality solution. That solves my problem. In the next slide, I will teach you how to find the minimum point on a quadratic function. So how to find the minimum of a quadratic function. But before I just give you the recipe for finding the minimum point of a quadratic function, let's do an example. So let's pick one concrete quadratic, 3x squared plus 2x plus 1, and let's find the lowest point on the graph of that quadratic. How do we do that? Well, we're going to do that by completing the square. Now you're going to say, well, but isn't the lowest point on a quadratic which opens up the tip of the parabola? The answer is yes, of course. But let's for a moment pretend that we do not have that extra knowledge, and let's just find the minimum point on that curve by completing the square, right? Also, the problem instructs us to complete the square. So anyways, we have to complete the square in order to complete the problem. So we may as well forget our knowledge about the tip of the parabola and just complete the square. So let's do that. So I have my quadratic, 3x squared plus 2x plus 1. I'm completing the square. If you remember, when we complete the square and then there's a leading coefficient, our first task is to factor out the leading coefficient. So when I factor out 3 from 2, I get 1/3. Right? So when I factor out 3 from 2, I get 2 times 1/3. Right? So when I uncover the parentheses, I'm getting 3 times 2/3. The 3 cancels, and I'm left with 2. Okay. So now, what do I add and subtract so as to make this into a perfect square, right? I'm trying to complete the square. So what do I add and what do I subtract so as to make this expression here into a perfect square? So how should I select the question mark so as to make that a square? I'm sure you guessed it correctly. I need to take the number that I see here, which is 1/3. I need to square it and I have to add and subtract it. So 1/3 squared minus 1/3 squared. That's what I need to add and subtract. So I'm taking this number 1/3 and I'm squaring it, adding and subtracting it. And as you can see, I've already simplified 1/3 squared to 1/9. Okay? Now, this becomes a perfect square, that is x plus 1/3, the whole thing squared. Now, let's uncover the parentheses a little bit. 3 times negative 1/9, that is negative 1/3. You can uncover the parentheses. And finally, I can combine these two terms to get 2/3. One more thing, this plus I can rewrite it as minus and minus, and 1 minus negative 1/3, that is 2/3. So my completion of the square is complete. Just a reminder, when we complete the square, we always want to have our standard form of the quadratic, which was a times x minus k squared plus h, right? To complete the square means to rewrite my quadratic into this form. I always want to have a minus here when I complete the square. Okay. Okay, so let's find the minimum point on the graph of our curve. What's that minimum point? What's its x-coordinate? sure you guessed it correctly. The x-coordinate on my minimal point is negative 1/3. And if you remember, that was just the number minus b over 2a, right? We already studied that, but here we did not need to apply our knowledge of the fact that the x-coordinate of the tip of a parabola is at minus b over 2a, because we were asked to complete the square. And because we were asked to complete the square, we didn't need to use any extra knowledge, because the number negative 1/3 just naturally appeared from the computations. It is x, whatever is subtracted from x in the completed square, that's the number we need to put there. And if you remember, we had also a ready-made formula for the tip of the parabola, for the y-coordinate of the tip of our parabola, but we don't need to remember that either, because that number is automatically given for us there. So the minimum point on our parabola is negative 1/3. Is its x-coordinate, and its y-coordinate is 2/3. Our problem is solved. Suppose we have a quadratic function, something like ax squared plus bx plus c. In the preceding example, we saw how to find the minimum point on the graph of that quadratic function. How did we do that? We first completed the square, which was done like so. This was, if you remember, the general theory of completing the square. And then, how did we conclude in the preceding example that we actually had the lowest point on the graph of the quadratic? Well, let's think about it. We had an expression of the form a times x minus b over 2a squared, but what's important is that this expression here is a square, right? So this expression here is a square. So I'm having a times a square minus d over 4a, right? So that's the situation that I'm at. So I'm guaranteed that a square is always positive. So I'm guaranteed that if a is greater than 0, so I'm guaranteed that if a is greater than 0, this entire expression here is always positive. So I'm guaranteed that the graph of my function, the value of my function, can never drop below negative d over 4a. So once again, if this a here is greater than 0, then I'm guaranteed that the value of this, so this entire expression here is positive. So I'm guaranteed that the smallest that this quantity can be is when a times the square is actually equal to 0. If the square is actually equal to 0. If this, because the square cannot be negative, so the smallest it can get is 0. So the quantity that I have boxed here can never drop below negative d over 4a. Similarly, if my a here, my leading coefficient, is negative, then the square is still positive. Negative times positive is negative. So if my leading coefficient is negative, the value of my quadratic can never exceed negative d over 4a. Right? So if the leading coefficient a is negative, so if the leading coefficient here is negative, my quadratic can never attain a value larger than negative the discriminant over 4a. So let's summarize this observation into a mathematical statement. If the leading coefficient of my quadratic is positive, then my function, my quadratic, has no maximum, because it opens indefinitely, it grows infinitely large. So if the leading coefficient is positive, then my function has no maximum, and has a minimum attained at the tip of the parabola, which is given when x is equal to negative b over 2a. If my leading coefficient a is negative, I have a parabola which opens down, and then that function has a maximum when x is negative b over 2a. In both of these cases, the actual extreme value, so the actual extreme value, so this height, the height of the extreme point, so this is the extreme value. So that's, in both of these cases, that's negative, the discriminant over 4a. In this case, the extreme value is this distance here. So this distance, this vertical distance, is negative d over 4a, that distance. The topic of maxima and minima of quadratic functions is very well suited for word problems. Let me show you one such text problem. Let x and z be two numbers that add to 12. So I'm having two numbers that add to 12. The numbers are called x and z. Let's choose x and z so that their product, x times z, is the maximum possible. Okay, so we read our problem. Now let's try to formulate the various statements of the problem into formulas. So let's do that. First of all, what are we trying to do? We're trying to maximize the quantity x times z. So we're trying to make this as large as possible, x times z. What are we given? We are given that x, the sum of the x and z is 12. So we're given that x plus z equals 12. Well, now we don't know how to maximize a function of two variables, but this is not really a function of two variables, because see, if x plus z is 12, I can actually solve for z. I could transfer x to the right hand side, and then I'm getting that z is 12 minus x. In this way, I have eliminated z. I have boiled down the expression to an expression which depends solely on x, right? Because z must be replaced with 12 minus x. So I'm trying to maximize x times z, but since z is 12 minus x, I'm actually trying to maximize x times 12 minus x. So let's uncover the parentheses. X times negative x is negative x squared, and 12 times x is, well, 12x. So I'm trying to maximize the function negative x squared plus 12x. But that is a parabola. So a parabola which opens down, right? Because its leading coefficient is negative 1. This is so negative x squared, that's in fact negative 1 times x squared. So the leading coefficient a is negative 1, so the parabola opens down. So since it is a parabola which opens down, it has a maximal point, and that's going to be for the values of x and z for which that maximal point is attained. That's going to be the answer to our problem. I want to just point out that if the parabola, so when we uncovered all the parentheses, if the parabola was opening upwards, then our parabola wouldn't be having a maximal point, in which case the problem would be incorrectly posed, because we wouldn't be able to choose x and z so that we get a maximal value for x times z. But because the problem was formulated the way it is, we got a parabola with a negative leading coefficient, hence we know that it has a highest point. Okay, so our parabola has a maximum, and where is it attained? Well, it is attained, actually, let me ask you, where is the maximum of that parabola attained? I'm sure you guessed it correctly. The maximum of the parabola is obtained at minus b over 2a. right? So, well, what's b and a? Well, b equals 12. That's the coefficient of x, and a is equal to -1. A is equal to -1. So 2 times a is actually equal to -2. So 12 divided by 2 is 6, and minus times minus is plus. So this cancels down to 6, and my final answer is x equals 6. What about z? Well, z is 12 minus x. X we just saw was equal to 6, so z is 6. That's it. The problem asks us for the values of x and z, and we got them, 6 and 6. Actually, let's read the precise formulation of the problem. Choose x and z so that the product is maximal. It is not completely clear what's our final answer. Do we just need to give the value of x? Do we just need to give the value of z? Or the value of z, the value of x, and the value of the product? When that's not completely clear from context, just indicate everything. So in this case, we indicated what x is 6. We indicated what z is, that's equal to 6. And let's indicate the maximal product. The maximal product is x times z, which is 6 times 6, which is 36. So our maximum is attained when x is 6, z is 6, and their product is 36.